Okay, hello, how are you? How are you doing? It's me, the pioneers in methods, Mourad Sultan Ezouidi. Today we are going to explore a method. Sorry, it's silent. So here we told that today, my colleagues, professors, teachers, we are going to explore a method that completely defines how we solve high-degree problems. It's really theorem. This method allows us to derive exact symbolic solution for polynomials that traditionally pose significant challenges. We will be solving a degree of 14 to demonstrate how Ezouidi theorem works, and we will compare it with classical numerical methods to highlight the power of this approach. So let's start, my professor. So prepare your pens and your paper sheets, and you are going to work at the same time the Professor Mourad Sultan Ezouidi is explaining. Okay, I will share the lecture with you, so that will be benefit from this new knowledge, new approach, new recursive formula that will help you to solve this 14th degree polynomial equation. Okay, so here we can see the coefficient of our original 14 degree polynomial equation are written as that. L0 is equal to 14, L1 is 91, L2 is equal to 364, L3 is equal to 1001, L4 is equal to 2002, L5 is equal to 3003, L6 is equal to 3432, L7 of ODQ is 3003, L8 is going to be equal to 2002, L9 is going to be equal to 1001, L10 is going to be equal to 364, and L11 is going to be 100, L12 is going to be 32, and L13 is equal to negative 10. Let's begin by examining the polynomial equation we are working with. Here is our degree 14 polynomial. Okay, is our degree 14 polynomial. Here, the example 6, we will solve it right now. So, P of x has to be equal as x to the power 14 minus 14 x to the power 13 plus 91 x to the power 12 minus 364 x raised to the power 11 plus 101 x to the power 10 minus 2002 x to the power 9 plus 3003 x to the power 8 minus 3432 x to the power 7 plus 3003 x to the power 6 minus 2002 x to the power 5 plus 1001 x to the power 4 minus 364 x to the power 3 plus 1000x times x squared minus 32 minus 10 equal a no. So now let me show you how Ezouidi theorem solves this problem exactly. We begin by expressing the polynomial as that P of x is equal to x to the power 14 minus L0 of order x of order q x to the power 13. You can see here L0 is 14 plus L1 of order q x to the power 12. L1 is going to be 91 minus L2 of order q x to the power 11. L2 is going to be 364. L3 times x to the power 10. L3 is 1001 minus L4 of ODQ x to the power 9. You will equate this, it will be 2002, plus L5 times x8 minus L6 x7 plus L7 x to the power 6 minus L8 x to the power 5 plus L9 of order qx4 minus L10 of order qx cubed plus L11 x squared minus L12 times x plus L13. So this is a 14th degree problem equation. Not this is not a second degree or the third degree or a fourth degree or a fifth. This is a 14th degree problem equation. And today the Professor Mourad Sultan Ezouidi will use his recursive formula. Okay, and we'll solve this right now. Okay, here you can see my professors here. It's here is the polynomial we are solving today. As you know, you can, as you know, you can see it's a 14th degree polynomial equation. Traditional method would rely on numerical approximation, but we are going to approach it systematically using my theorem. First, let me point out something key, okay? And you will see the alpha subscript k equal a 0 of O the cube plus x subscript k divided by n denotes the highest power, the degree of this 14th degree. So the expansion, or let's say the explanation here in this context should provide a solid understanding of the challenges classical method face when solving high degree polynomial equation, and how Ezouidi theorem offers a promising alternative. My method, based on Mourad Sultan Ezouidi theorem, excluded all the classical methods, including Abel theorem, which states that certain polynomials can't be solved using radical. Contrary to Abel's assertion, my method demonstrates that even polynomials with radical roots can be solved exactly. When traditional approach failed, my theorem reveals the exact symbolic roots through a structured process that bypasses the limitation of classical algebra and numerical method. This is not just numerical approximation. It provides precise, solvable roots for polynomials that would otherwise be deemed insolvable. Okay, so I will continue my professors to let you get the point how this 14th degree polynomial equation solved by using the theorem of Mourad Sultan Ezouidi, the or the let's say or the recursive formula. Okay, so here we told before that this is a 14th degree. To find out the roots of this polynomial, we should determine the values of SR for the Q relative respectively to LR, where R belongs to a set of numbers from -1 up to 14 minus 1 means up to 13. So here we start with uh, with telling the following. Traditional method for solving polynomials often involve numerical approximation, which can be quite error-prone, especially when we are dealing with high-degree polynomial equation like this one. Numerical method here, such as Newton method, gives us approximation of the roots, but these come with the risk of rounding errors and can't guarantee exact value. But here, professors, teachers, and colleagues, we can say that. But with the Ezouidi theorem, we approach the solution differently. This theorem allows us to break down the polynomial and solve for the roots symbolically. It involves a recursive process that systematically finds the exact values of the roots, avoiding any of the errors that arise from approximation. Here, the theorem of the Professor Mourad Sultan Ezouidi is written as that sk minus 1 of order r equal the sum from 0 to k combination n minus r, choose k minus r, n raised to the power r between parentheses negative and 0 of order q raised to the power k minus r times lr minus 1 of order q. Here, this is the recursive formula that will help you to find out the new 14th degree polynomial equation relative to the, or corresponds to the original 14th degree polynomial equation. Here is the formula that we will use to compute the roots. Let's break it down. You can see this one, combination n minus r choose k minus r. These are binomial coefficient that adjust the terms. And here n raised to the power r, this terms means the will raise the degree of the polynomial. And here negative L0 of order negative L0 of O dq, all raised to the power k minus r, denotes or involves the base coefficient L0 of O dq adjusted by the power of k minus r. And then the coefficient of my original 14th degree polynomial equation refers to the earlier terms in the polynomial as you proceed through the recursion. Okay, so here, now let me show you how Ezouidi theorem solves this polynomial exactly. We begin by expressing the polynomial as that p of x equal, okay, and here we can, if you are going to see this standard form of 14th degree polynomial equation, has to be written as x raised to the power 14 minus L0 x 13 up to L13 of 4q equals 0. So here, when we can then apply the recursive relation set and symbolic transformation to derive the exact roots. Here is the step-by-step process. First, we express the equation in terms of sk minus r of O the q, which is a set of symbolic coefficients that we can recursively calculate. These coefficients are based on the coefficients of the 14th degree from the equation. As we proceed, we calculate each as k minus 1, which directly relates to the roots of the polynomial. The key here is that every coefficient sends you a message. Every coefficient tells us a message, and every coefficient is determined symbolically without any numerical approximation. And these coefficients that tell us, let's say, message, we should know how to listen to this coefficient. Okay, so for this polynomial, we calculate the symbolic roots. In other words, we have S0 is equal to 0, okay, up to S11 is going to be equal 91 times 14 raised to the power 12, and S12 is 0, S13 is 0. Means we collapsed this original 14th degree polynomial equation to be written as x raised to the power 13 plus S11 x raised to the power 3, okay, squared, because 14 raised to the power 12 here. So a squared equals 0, okay? And we now the recursive calculation of the coefficient ensures that we are working with exact symbolic values. Means here this theorem does not is not here to approximate or to estimate roots. No, this theorem does not approximate, does not do approximation. This theorem solves 14th degree polynomial equation and will give you exact symbolic roots. Okay, in one set if you want. Okay, not in separate sets of roots. No, in one set we can put all the roots in one set. Okay, so here, professors, we told that we continue now. I'm going to apply this recursive formula for this 14th degree polynomial equation, and we told that k equals 0, s minus 1 is 1. K equal 1, s0 is equal to 0, according to the formula after developing it. And we are going to use the coefficient of this original 14th degree polynomial equation, and we will find the value of S0 is equal to 0. Here, again, dive into the structure, into the recursive formula of Mourad Sultan Ezouidi, and put k equal to. To put k equal to, you are going to derive the second coefficient of this new 14th degree polynomial equation that has been derived from the formula. Okay, this is the formula, professors. You can see this is the formula that will give you the value of S2. Okay, it will be combination 2 choose 1, combination n choose 3 as cubed minus n minus 2 choose 1 times n squared L0 times L1 plus n cubed times L2. So this is the second. This formula will give you the third. Yes, when k equal 3 here, when k equal 3, yes, means you are going to find the third coefficient. Okay, so direct application, or substitute L0 and L1, L2 in the formula, and we'll obtain the value of this S2 here is going to be equal to 1. Now we continue, professors and colleagues and teachers and students And so learners and those who have smart mind, those who want to go deeply into the research, into the method, into this approach, you are welcome to be benefit from this research, from this whole demonstration that we that this recursive formula, this theorem solves, let's say, a 14th degree, also solves 13th degree, also solves 11th degree, also solves 12th. Okay, means up a linear equation up to nth degree. Okay, this is no problem. Now we can continue. Okay, now I'm going to find the fourth coefficient of this new 14th degree from the equation. Just apply the Ezouidi theorem or the recursive formula of Mourad Sultan Ezouidi and find the formula that will give you the fourth coefficient. Okay, this is the formula, depends on L0 and L3 and the highest power. Okay, so S3 index with 3. Okay, S2 index with 2, and so on. Okay, so here, professors, we are going to calculate it to substitute in this formula, and we obtain that, in fact, S3 here is equal to 0. You can put your own these values in your scientific calculator, and you will figure out that is going to be equal to a no. We continue now. We told that I'm going to find S4, means I will try to find the fifth coefficient of this new 14th degree from the equation that corresponds to the original 14th degree from the equation. Here, the recursive formula or the theorem of the Professor Mourad Sultan Ezouidi, and this formula S3 here will give you the fourth coefficient. Just calculation, do your best, and write the value of this S3 here. In our example, is going to be equal to an L. Okay, equal to 0. Okay, means we collapsed it. We collapsed a 14th degree polynomial to be written as x to the power 14 plus something x to the power 7 plus a real number of plus any other number. Okay, so here is the key of the work. Okay, to simplify this 14th degree from the equation for you and to let you solve it in be let's say and be quiet by using the recursive formula of the Professor Mourad Sultan Ezouidi. So here S3 we told that is equal to 0. We told I'm going to find I want to find the S4. I should put k equal 5 in the recursive formula or in the theorem of the Professor Mourad Sultan Ezouidi, and here S4 is going to be equal to k equal to what? Just I will make something here. Okay. So here we told that uh, S4 is equal to the last formula. You see this one L0 raised to the power 5. It's a common factor here. What is it? Here, and here. And the difference between the binomial coefficient when r equals 0 and r equal 1, it will be positive. It will be combination 1 choose 4 times combination 5 choose n times L0 of O the q raised to the power 5. Let's see it here. Yes. So here it will be, yes, combination 4 choose 1 and choose 5 times L0 raised to the power 5 minus, here we started with 4, I should terminate with 4. Okay. So this will give you the fifth coefficient of this new 14th degree from the equation. Okay, so what's needed here? You use L0 up to L4. Means you are going to use just L0, this one, and that, and this, and that, and this. And you start. This will give you exactly the fifth coefficient of the 40 of this new 14 degree polynomial equation. Now, professors, we continue. We thought I will calculate this. I calculated this, in fact, and it's going to be equal to an L. So here, to find k, to find S5, just put k equals 6 in the recursive formula or in the theorem of Mourad Sultan Ezouidi, okay, and do your best. After deriving after deriving this formula, that will give you the sixth coefficient has to be written as that. Okay, just calculation and put the values of L0 and L1 and L2 and L3 and L4 and L5. Here S5 has to stop. You should stop at 5, L5. If it is N, you should choose at N, okay? And this is the key. So here are the coefficients. Why I wrote this in order to let you know that this coefficient belongs to this original 14-degree polynomial equation that we started with, okay? We go step by step by making substitution and substitute L0 with 14, L1 with 91, L2 with 364, L3 with 1001, L4 with 2002, and L5 is 3003. Here is going to be equal to now. You can put 14 raised to the power 6 as a common factor. Just write the binomial coefficient, okay? Okay, all of this. This is binomial coefficient. This is binomial coefficient. This is binomial coefficient 364. Okay, 364. Where is it? 364. Okay, this one. Yeah, this one. 364. Okay, so uh, okay. Now, just calculation, you will find that is equal to 0. Now, for k equals 7, we want to find S6. We go to substitute k equals 7 in the theorem of Mourad Sultan Ezouidi. And here, after expanding this and simplifying, the professor, let's say, explained the and written the S6 has to be written as that. Okay, started from 6, should stop at 6. Okay, means if the coefficient that will be need here is from L0 up to L6, means 3432. Do your best and calculate this. You'll find the value of S6 here is going to be equal to 0. Okay, means we collapsed all the coefficients of this in the 14, the original 14-degree polynomial equation to be written as x raised to the power 14 plus s11 x raised to the power 2 plus another constant will be 0 or not. Okay, this is the meaning of collapsing, okay, reducing the polynomial to be solved. Okay, so we continue, professors. We told that when k equal 8, I'm going to find the 7. Just put k equal 7 in the recursive formula of Mourad Sultan Ezouidi, and you will obtain to get to write this formula that will give you the 8th coefficient. This is its formula for any degree polynomial equation. Okay, this is a formula. Relate S7, sk minus 1 with the binomial coefficient and with L0 for the q raised to the power r minus 1, k minus r, and with lr minus 1. Okay, so means this S7 is the new coefficient related or relative or corresponds to the original 14-degree polynomial equation. Okay, we continue here. I will apply this formula and I will calculate this. Then the value of f7 here is equal to n. Now, to find the 9th coefficient here, professors, you should at least replace k with 9 in the theorem of Mourad Sultan Ezouidi and write this after simplifying and write it in its lowest term like the professor was doing here, as 8 is equal this formula. Okay, so we should substitute L0 with its value up to L8. These are the coefficient up to L8, means you are going to use only the first ninth coefficient. Okay, so then what's needed here, I'm just substitute this formula. This is the formula. You see 8, 1, 14, 9. Here is written n because n is 14. 14 raised to the power 9 minus 12, 7. Why? Because 14 minus 2 is 12. Choose 7. Okay, we apply this formula here and you will get that the value of this is equal to n. Okay, so you can see that this theorem is not only, let's say, is not only a powerful theorem, powerful method or approach. It's opened the door for giving, for finding out the the exact sample proofs with no approximation. Means here in this context, in this topic, in this 14th degree polynomial equation, we solve, and give exact values for this 14th degree polynomial equation. Otherwise, unlike ChatGPT and the AI, artificial intelligence and DeepSeek, both of them, they tackle the polynomial, but they told we can't do this, okay, because they can't do this because they don't have computational tools. Okay, so here is the Professor Mourad Sultan Ezouidi with you now. Okay, to let you understand that symbolic roots for an n degree polynomial equation can be reached and can be solvable. Okay, solve it for me. So now we told that S8, the ninth coefficient is 0. We put k equal 10 in the recursive formula and try to find the value of S9 because 10 minus 1 is 9. Okay, the k sk minus 1 of I equal the sum from 0 to k combination n minus r, choose k minus r n raised to the power r between parentheses negative L0 42 raised to the power k minus r times L minus 1. LR minus 1 of 42. Here, what's needed exactly, put k equal 10. You will obtain S9 because 10 minus 1, k is 10, k is 10, k is 10. Okay, now I will expand this and put L0 of order q raised to the power 10 as a common factor and calculate the difference between the first two binomial coefficients when r equals 0 and r equals 1. I will find that the value of this difference as 9 will be negative combination 9 choose 1 times combination n choose 10. Okay, like that here. Okay, yes, this one is negative combination 9 choose 1 times n choose 10. Okay, for me, I don't have problems because this is the formula and I already know how it works and how S9 has to be started with and S8 has to be started with and whatsoever. Okay, means S odd number has to be negative, means that the first S subscript odd number is negative sign and S even number or the R has to be started with positive sign. So you can put here in your mind like minus 1 squared is 1 and minus cubed is minus 1 cubed is minus 1. Okay. So here, Professor, we call that, sorry, comes here. Yes, I calculate this. You see the calculation. I will use this formula as it is, okay? The formula that has been derived from the recursive formula of Mourad Sultan Ezouidi. And after writing this formula in its lowest term, and after making L0 42 raised to the power 10 as a common factor and make the difference, calculate the difference between the two first binomial coefficients, and you will get that S9 here is equal to this, is equal to now. You see, so here, professors, we continue to find the 11th coefficient of this new 14th degree polynomial equation. Okay, so when k equal 11, this has to be written as that, as 10. The sum from 0 to 11 combination n minus r choose 11 minus r, and n is 14. Write the formula first in terms of n because you are working with nth degree from the equation. And if n is 14, put 14. If n is going to be 2, put 2. Okay? So we continue. 2 is not possible because 2 is less than 11. Okay, from 11 and okay. Times n raised to the power r between parentheses negative L0 42 raised to the power k minus r times LR minus 1 42. Okay. Here, professors and teachers and colleagues and my learners, my student, stand after writing it in its lowest term, these will give you the 11th coefficient of this new 14 degree polynomial equation. Okay, means a mathematician or a researcher or a professor or whatsoever you are, in order to find the 11th coefficient, you should apply the formula. You should apply the theorem of Mourad Sultan Ezouidi, okay, and calculate it. And these formula, not only S7, S9, S10, S11, Okay, these formulas are general, have been generalized for any n degree polynomial equation, means Sk denote the coefficient of this new 14 degree polynomial equation, and La is denote what? Denote the original 14, the coefficient of the original 14 degree polynomial equation, and this is the theorem that relate the new 14th to the original 14th. Okay, to what? Because you see sk minus 1 and lr minus 1 inside, there is a relation between sk minus 1 and lr minus 1 because they hide there the symbolic roots. The symbolic roots are between. Okay, are between. Okay, thank you. Anyway, yeah. So we continue with all that. I'm joking. Eh? Okay, so here, what's needed exactly? You will use L0 up to L10. What is L10? This is L10 up to 364. You will use all the previous coefficient. And if you want to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. That's why here, if you go back, when k equal 11, you see this one? When k equal, sorry, when k equal 11, means you will try to find, or you are going to search for the values of S10, because 11 minus 1, okay? So, with all that, boys, here, S10 is going to be equal to negative combination. Okay, and choose 11. Okay, time is the common factor. This is the common factor here. Okay, I put outside. And the difference between the first two terms, the first two binomial coefficient is gonna be equal when r equal 1 and r equal 0. It will be combination 10 choose 1 times n choose 11. Did you remember when I told you S subscript even number? 10 is even number, so it will be positive. If it is 11, it will be negative. If it is 12, it will be positive, and so on. Positive, okay, here. Okay, this is minus, plus, yes. Okay, this is 10, huh? Okay, plus, minus. This is minus. This is minus. Okay, minus. Sorry. This is minus. This is a plus. Okay, minus. This is a plus. This is minus. This is a plus. This is minus. This is a plus. Sorry. This is minus. Okay. And then this one is n minus 10. Here is n minus 10. Okay. 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 So I will share the screen with you, entire screen. Okay, and also share system edu. Okay, now we told that here, you see, we told this is minus 10 instead of uh, pushing or put my fingers on delete. I put on the switch off. So this is delete. Okay, n raised to the power 10, n raised to the power 10. Okay, then this is n, this is L8, this is L9. No, it's correct. Okay, plus, okay. I will apply this formula, professors, to find the 11th coefficient. I will go back. You see this one, this is the formula. Here, yes, it's corrected. Minus n minus 10, n raised to the power 10, L0 raised to the power 1, and 9. Okay, I comes here up to check this one. Okay, here, yes, correct. It's the same, you see. I will try to uh, go here, delete. Okay, you see now, N11, and here N11, L9, L9, L0 raised to the power 1, N raised to the power 10, minus combination. Okay, so same formula, no change. Okay, but here with the previous one, we just substitute the positive sign because it wasn't did like that. Okay, this is also the correct formula. We told that this is S even number 10, positive, minus, positive, minus, positive, minus, positive, minus, positive, minus, positive. Okay. Now just calculation here, professors, you find the value of this one has to be equal to now, okay. For k equal 12, we write use Mourad Sultan Ezouidi theorem, and we substitute k equal 12, and we obtain the here as 11. This is the formula, professors. You see, this is my best colleagues, my best teachers, and students and learners, and those who have smart minds. This is the formula that will give you the 12th coefficient. Okay, so something new for you. You didn't see this before. Train yourself. This is a chance, an opportunity is open for you to learn, for you to learn from new, okay? To get rid of the usual method, classical method, method of Newton, iterative method, means they find approximation, approximated roots or guess worked or estimated roots with iteration method. Iteration, yes. Try, like a try, the first guess. I suppose that x equal to is a root. I will try it. If it is a root, so I'm going to differentiate this equation and see if it is also and so something like that. It's a called progression, like progression series. Okay, xn plus one equal, for example, uh, equal xn plus d of x and divide by xn, something like that. Okay, here, professors, we told we should continue. So I calculate the value of S11 here, in fact, which is equal exactly to 9 times 14 raised to the power 2. Okay, this is a calculation. Just you can use calculator, and you will see that the value of S11 here is 9 times 14 raised to the power 2, 12. Okay, means here, if we are going to go back to tell that x equal 1 is a double root up, I will try to come here up, but maybe I will lose this paper, but I will try to come here. Okay, okay, just give me time. Okay, so that can, okay, no problem. Lala, I should appear this for you. Okay, okay, okay. Here, you see, we told is 91 or 9, is 9. Okay, this one. So let's come here, check the coefficient. Okay, coefficient that we started with, and the polynomial. Okay, now we comes here. We told that when k equal to 12, we obtain 12. We reach, okay, this is 12. We told the value of this is equal to 9 times. Yes, 9 is 9. Okay. Now we continue. I want to find the 13 coefficient. Just put k equal 13 in the recursive formula of the Professor Mourad Sultan Ezouidi, and you will try to write S12 as this. This is the lowest. This is the general formula to find the 13 coefficient for any nth degree polynomial equation. Here is going to be equal to now. Just calculation. This one you can calculate. I will give you 1 minute to calculate this. Can calculate it. Okay. Clear. Now, professors, we continue. I want to find the 14th coefficient, the last coefficient of this new 14 degree from the equation that corresponds to the original 14 degree from the equation. Then I'm going to find out the x roots of this new 14 degree from the equation and write and go back to the recursive formula and write alpha k equal 0 plus 0.42 plus xk divided by n. N is 14 and xk is the x roots of this new 14 degree from the equation, and L0 is 14. Then I will find the exact symbolic roots of this this original 14 degree from the equation. So here we told that this is Professor 13 is equal combination n choose 14 times L0 of ODQ raised to the power 4 minus n minus 1 choose 13 L0 for the q raised to the power 13 times L0 for the q raised to the power 1. This is 14, common factor. The difference between this and that will give you negative combination 13 choose 1 times combination 14 choose n. N choose 14. After that, n is equal to 14. 14 choose 14 is 1. 13 choose 13 is 1, and so on, because it will be cancelled here. But me, I wrote it, you see here, combination n minus 2 choose 12. N is 14. 14 minus 2 is 12. 12 choose 12 is 1. Okay, this is, but this is written in general formula. This formula has been generalized for any nth degree polynomial equation. And n here denotes the highest power of the polynomial. If you are working with 20th degree, n is 20. Okay, if 100, and n is going to be of 100. Okay, and this, when for example you are solving 100 degree from the equation and you want to find the 14th coefficient, you should use this formula, you see. And 14th coefficient, 15th coefficient, it will be longer. The formula will be so long, but it should calculate it. Okay, so here we told that. Now I'm going to calculate this, the last coefficient I already calculated, and the value of this here is going to be equal to n. So here we can say that S0 is equal to 0, S1 equal to 0, S2, S3, S4, S5, S7, S8, S9, S10, but S11 is equal to 9 times 14 squared plus S12 raised to the power r equals 0, S13 equals 0. Now, professors, just here in this polynomial, instead of writing L0, I write S0, S1, write S1, and so on. Okay, so here I should continue. So, unlike traditional methods, which often use numerical approximations, Ezouidi theorem provides a precise symbolic solution. Okay, you can say that unlike traditional methods which often use numerical approximations, Ezouidi theorem provides a precise symbolic solution. This ensures that the roots we obtain are exact and not subject to the errors that arise with numerical method. Once we have the symbolic coefficient, we use them to find the exact roots of the polynomial. For this equation, we obtain, in fact, the following. Okay, sorry. Okay, for this equation, professors and teachers, we exact share for the speed. So here we told that uh, p of x has to be equal x raised to the power 14 minus s0 for the x raised to the power 13 plus s1 for the x raised to the power 12 minus s2 for the x raised to the power 11 plus s3 for the x raised to the power 10 minus s4 x raised to the power 9 plus s5 x raised to the power 8 minus s6 x raised to the power 7 plus s7 x raised to the power 6 minus s8 x raised to the power 5 plus s9 x raised to the power 4 minus s10 x cubed plus s11 x squared minus s12 times x plus f13 equals 0. This is the new polynomial that I obtained from the recursive formula. Now let's focus on the term involving s11, okay, which leads us to a simplified form of the equation. So p of x has to be equal to x raised to the power 14 plus s11 x squared equals 0. This simplifies further to x raised to the power 12 plus 9 times 14 raised to the power 12 times x squared. Now from here we can solve the equation. X squared is equal to 0, means that x equals 0 is root multiplicity with multiplicity 2, and or x raised to the power 12 plus 9 times 14 raised to the power 12 equals 0. Here x squared equals 0, it's obvious that x equals 0 is a double root. Okay, to find alpha for this x squared, write alpha 0 1 equal L0 q plus x, this one, x, which is 0 divided by 14. 14 plus 14 plus 0 is 14. Divided by 14 is 1. So x equal 1 is a double root for the original 14-degree polynomial equation. Now we'll solve this, okay? So we derive the following. X raised to the power 12 equal negative 9 times 14 raised to the power 12 times exponential 2k I pi. Here the minus 1, I will put it here inside the exponential raised to I pi, because minus 1 is equal to exponential I pi. Cosine cosine pi plus imaginary I pi, means cosine pi is minus 1, so it's written here. Now you see, this is x raised to the power 12. I want xk, means I will take, by taking the 12 roots of both sides, we get the roots. Xk for this new 14-degree polynomial equation is 14th times 9 raised to the power okay, raised to the power, yes, of course, here is gonna be, okay, yes, so I will make here 9, this is 9, this is 9, this is 14. Okay, now and 14 raised to the power 12, all raised to the power 1 over 12, it will be only 14. Then 9 raised to the power 1 over 12, it remains there. And I should divide the index in the base of exponential by 12. Okay, so here, this is exact symbolic roots for the polynomial. The roots are expressed in terms of complex exponential, which is a direct outcomes of the recursive steps we have followed. As you can see, Ezouidi theorem doesn't rely on numerical approximations. The roots we have derived are exact, not subject to the error-prone calculations that come with numerical method. This approach ensures that we can find the roots exactly, even for high-degree polynomials that are too complex for classical methods to handle. For example, here, uh, approximation method give x equal 1.234 to 3 decimal places, and the negative number negative 0.876. This is not a root, and this one is gonna not be a root. Okay, and but here you see that x has to be equal to 1 is a double root. Okay, but with the Ezouidi theorem we have xk equal 14 times 9 raised to the power 1 12 exponential 2k plus 1 I pi divided by 12. This, these roots can't be like that. Okay, can't be, impossible. Okay, so here the roots are derived recursively, where we solve for them step by step. These formulas break down the polynomial into manageable components, allowing us to derive exact symbolic values instead of approximation. Let's see how this works in practice. Notes here, because the recursive structure in Ezouidi theorem, we were able to derive these roots systematically and precisely without approximation. So this is our 14th degree polynomial equation. Now I will derive exactly the symbolic exact values, exact roots. This alpha k called the roots of this polynomial. Okay, equal L0 for the q plus xk. Xk here, professors, is the x roots of this new 14th degree polynomial equation. This one, this one, go back. This one, yes. Okay, which written x14 plus s11 x squared equals 0. So the xk is the roots of this. Okay, and alpha k we told is L0 plus xk all divided by 14. Okay, and here we told x L0 is 14, xk is 14 times 9 raised to the power 1 over 12 times exponential 2k plus 1 I pi divided by 12, all divided by 14. 14 over 14 is 1. 14 over 14 is this one, is the, means this ratio here, 14 times 9 exponential, all, okay, 9 exponential 2k plus 1 I pi, all divided by raised to the power 1 over 12. Okay, divided by 14 is 1. So these are the first 12th, the first 12th set of roots of this original 14 degree polynomial equation. Now the next two roots dependent on xk. We thought before x squared equals 0 means xk from 0 to 1 is 0. Therefore, L0 plus sk divided by 14. L0 is 14 and x0 is 0, double root divided by 14 is 1, is a root multiplicity 2. Okay, so you can see that here, professors, unlike traditional method, which often use numerical approximations, Ezouidi theorem here provides a precise symbolic solution. This ensures that the roots we obtain are exact and not subject to the errors that arise with numerical methods. Now that we have calculated the exact sum of roots, let's verify them like traditional numerical methods, which can introduce rounding error. These roots are exact. Okay, thank you for listening. This is the Professor Mourad Sultan Ezouidi. Thank you for joining us. Okay, and see you inshallah next time. Okay, thank you and goodbye. I will stop streaming. Okay, so thank you. This is the pioneers in methods. Mourad Sultan was with you. Now we'll end